All right, so now we're looking at case 2, which is the case where we have repeated real eigenvalues. And so for this, we need to be careful with some terminology. It's familiar terminology, but we just want to make sure that we're using it correctly. So first of all, because when you're finding the eigenvalues of a matrix, you're solving a polynomial equation, a thing that we call the characteristic equation. It's possible that we get repeated real roots, and from algebra we know that that's occurring when you factor that polynomial and you get factors like this, some linear expression to a power. And in particular, the terminology we're going to use is we're going to say that an eigenvalue, lambda k, for example, has multiplicity m if when your characteristic equation is when its polynomial side has been factored, you see a factor of this form, lambda minus lambda k to the m, where lambda minus lambda k to the m plus 1 is not a factor. Basically, that just means if you factor this completely, m is the highest power that we can represent this by. In particular, we're interested in the cases where the multiplicity of an eigenvalue is 2 or greater. So there's a few different cases to consider here. We're going to focus on 2, but let's start with this first one here. So let's suppose we have some n by n matrix A. Then it's always possible to find m linearly independent eigenvectors, k1 through km, corresponding to an eigenvalue lambda 1 of multiplicity m. So notice what it's saying here is we can find a set of linearly independent eigenvectors where the number of vectors in that set is equal to the multiplicity of that eigenvalue. Okay? And in that case, the general solution of the system contains a linear combination of this form. So, sorry, let me back this up a second. I think I said it's always possible. It's not always possible, but in the case where it is possible to find m linearly independent eigenvectors where m equals the multiplicity of your eigenvalue, it will appear in your general solution. So notice all this is a linear combination of your eigenvector time that exponential e to the lambda 1t, where lambda is the eigenvalue, lambda 1 is the eigenvalue corresponding to k1 here, and similar for all these other terms. So this looks very much like the case 1 case that we looked at. We haven't talked about how to find these linearly independent eigenvectors corresponding to that one eigenvalue. But we know that at least that the solution will contain terms of this form. Now the trickier case, which is not uncommon, is when you have an eigenvalue lambda 1, let's say, of multiplicity m, but even though m we're assuming is greater than 1, we can only find one eigenvector corresponding to that. So this sometimes occurs as well, where you have, for example, let's say an eigenvalue of multiplicity 2, but you can't find 2 linearly independent eigenvectors, which is what you need for your solution. You can only find one. In a case like that, we can construct additional solutions out of our one linearly independent, or sorry, out of our one eigenvalue, and those new solutions that we construct will be linearly independent when we put them into a set. So the first, let's suppose that k11 is the eigenvector corresponding to the eigenvalue lambda 1. Okay, so one solution that we could form in a case like this is x1 equals that eigenvector times e to the lambda 1t. So a familiar looking term there. Now, once I've done that, I've used the only eigenvector that I was able to use, because we're assuming that only one was able to was available. So the next thing that we do is we construct a new term with 2 new vectors, k21 and k22. And I'm going to talk about a couple of cases after this that show how to find these 2 vectors using k11. But notice what they're being multiplied by, t e to the lambda 1t and e to the lambda 1t. It's lambda 1 in both cases because that's the only eigenvalue that we have to work with here. And then beyond that, you see this dot, dot, dot. It kind of says there's a pattern occurring here. And we see something that kind of resembles like a Taylor series almost, where if we get down to xm, the multiplicity of this eigenvalue, then we're going to have terms of this form. So km1, where that's some vector that we'll talk about how to find, t to the m minus 1 over m minus 1 factorial, e to the lambda 1t, and then you can kind of see this pattern here. So for us, we're not going to be dealing with anything, any eigenvalues with a multiplicity greater than 3. So even though this argument can apply to much higher multiplicities than that, we're not going to have to deal with that. So this very complicated looking formula here, the worst it's going to get for us is the case where m is equal to 3. Okay. So I want to talk about the two cases then. That being the case, we need to look at what to do if we have an eigenvalue of multiplicity 2, but only one eigenvector is available, and what to do if we have an eigenvalue of multiplicity 3, and only one eigenvalue is available. And I already see that I made a typo. This is supposed to be a 3 down here. Here we go. So, like I said up here, let's suppose that we have an eigenvalue, it has multiplicity 2, but we can only find one eigenvector. And we're going to call that eigenvector k, all right? So I'm going to say one eigenvector k. Now, what we need, because this eigenvalue has multiplicity 2, we have to find two linearly independent solutions to our system that are associated with this eigenvalue. And one of them will take this form, where that k11 is just the k that's showing up here. So we can get one solution right away once we have that eigenvector by just doing k times e to the lambda 1t. But coming up with that second eigenvector is the tricky part. Second solution. So what we do is we construct a second solution that takes this form. Notice this is the form that we're saying we can find a second solution with. And it takes the form of some vector times t e to the lambda 1t plus another vector times e to the lambda 1t right there. We're not going to kind of show how we found this, but we're going to verify that it works. So the two vectors that are going to show up here and here, the first one is the same eigenvector that we found, k. The second one is some unknown vector, p, which we'll solve for once we've found k. So if we were to take this expression, and again, we're assuming it's a solution to this homogeneous system, x prime equals ax, we can substitute that in to this, and that would give us this expression right here after some simplification. I'm skipping the steps that show all this, but this would be what that system looks like if we substituted everything in. Now this would have to be an identity. It has to be true for all values of t, which implies that the vectors that are in the parentheses here, those would both have to equal 0 if this is supposed to be equal to 0 as an identity. Now this set of things in the parentheses here, if we set this equal to 0 and we factor that k out, putting an I in here like we did before, identity matrix, then that would say that a minus lambda 1 ik is equal to 0. And this looks like how we would find an eigenvector in the first place. Now this one right here, if I set this expression in parentheses equal to 0, then I could add a k to both sides, and what remains has p's here. I could factor that p out using the same technique as before, and now I get a minus lambda 1 p equals k. So if I know k, I can put k into this equation and solve for the vector p. We're going to show how that works. All right. If instead we have an eigenvalue with a multiplicity of 3, and still only one eigenvector can be associated with it, then we can walk through a similar argument as what we showed up here and show that we can get one solution of this form, which again is that one eigenvector being shown here times e to the lambda 1t. We can get a second solution using this, what we just talked about. And then we can get a third solution, which would take this form, and the p and the q, those two vectors are related by these equations. So again, this is the same, these first two equations are the same ones that we got here. Q is going to relate to p, a minus lambda 1 iq equals p. Okay? And we're not going to walk through that argument because it's similar to what we did there. It's just time consuming. So that, I know that feels like a lot. So we're going to walk through a couple of examples to illustrate this. I'm going to start with this system. I'd like to solve this 3x3 system. Okay? So the first thing that we need to do is find our characteristic equation. And remember our characteristic equation, again, we're going to call this A, is the determinant of A minus lambda I equals 0. And in our case, that determinant would look like 4 minus lambda, 1, 0, 0, 4 minus lambda, 1, 0, 0, 4 minus lambda. Now you could find this determinant using cofactor expansion, and go for it if that's how you want to do it. There is a little trick we can use in this case. This is something you would learn in linear algebra. This is what we call a triangular matrix. Specifically, it's an upper triangular matrix. A triangular matrix is a matrix that has all zeros either below its main diagonal or above its main diagonal. And you notice here, the main diagonal is these terms right here, the 4 minus lambdas appearing here. Below that are all zeros. Triangular matrices are very easy to take determinants of because the determinant of any triangular matrix turns out to always be the product of its diagonal entries. So this is literally just 4 minus lambda times 4 minus lambda times 4 minus lambda, or 4 minus lambda cubed. Okay? If you do that with cofactor expansion, you'll get the same result. So this means that lambda equals 4 is the only eigenvalue that we get from this matrix, but its multiplicity is 3, because that's the exponent that I'm seeing there. Multiplicity is 3. Okay? So what we need to do is find an eigenvector associated with this. If we're looking at the eigenvalue of 4, that means I'm plugging a 4 in to the lambdas in my matrix here. Now, I'm going to use a different notation for this one because it's what your book uses, and it's the more common notation if you're using, if you're solving systems with in linear algebra. It's Gauss-Jordan. So if you're not familiar with Gauss-Jordan, basically what I'm doing is I'm plugging my 4 in for the lambda in my matrix here. Notice that would give me 4 minus 4, which is 0, 1, 0, and then I'm going to have 0, 0, 1, 0, 0, 0. Then I'm going to put a vertical line. I'm going to put the constants that this system is supposed to be equal to, 0, 0, 0. Okay? And what I'm doing here is I'm trying to solve this for k. So the 0 vector showing up here is why I'm getting zeros here. Now, think about what this is. This is a coefficient matrix on this side. And so this is 1 times k2. This is the second column of this matrix, so it corresponds to k2, which equals 0. And here I have k3 equals 0. So k2 and k3 are both equal to 0 in this system of equations. K1 drops out of all of my equations. And what that means is that K1 is anything I want it to equal. So I can actually just set K1 equal to 1 to keep things simple. That means that the eigenvector that I'm looking for here is K equals 1, 0, 0. Okay? So that wasn't so bad. Now what I need to do is move on to this equation here, okay? Because this is going to be how I find my next... remember, we have multiplicity 3 here, so we're looking for 3 solutions. We just got the eigenvector that'll give us one of them. The second solution is going to take this form, and the third solution will take this form, which means I need to know what those vectors p and q are going to be. P comes from this linear system. Notice it has the same coefficient matrix as the previous system, but now this p, this coefficient matrix times p will equal the matrix k instead of 0. So what I'm doing is I'm setting up the same coefficient matrix that I did here, but instead of 0, 0, 0, I'm going to use k, which is 1, 0, 0. And so what that looks like is this: 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0. Okay? Now let's think about what this means. 1 times k2 equals 1. So that means that k2 is equal to 1. 1 times k3 is equal to 0, which means k3 equals 0. And then once again, k1 doesn't appear in any of our equations because it's being multiplied by zeros. So that means k1 can equal anything I want it to. I'm going to set k1 equal to 1 for simplicity. But you can literally set it equal to anything you want. That means that my matrix P is equal to 1, 1, 0. And you know what? I'm going to change this up a little bit. I don't want to use k's here since I already use k's up here. Since my matrix is called P, let's use lowercase p's. Let's call that P3. And call that P1. Okay? So here's that second matrix P. Now, I need to find a third matrix or third vector, Q. Q is this guy right here. Okay? And I use the same coefficient matrix, but now I'm setting it equal to P, which I just found. So I'm taking my same augmented matrix, which is what we call this, 0, 1, 0, 0, 0, 1, 0, 0, 0, and now I'm putting as this last column 1, 1, 0. Okay? Once again, well, let's call these Q's since the matrix is going to be called Q. So this column is Q1, Q2, and Q3. This equation up here would say Q2 equals 1. And down here, I'm also going to have Q3 equals 1. So Q2 equals Q3 equals 1. Once again, I can set my first unknown Q1 equal to anything I want. So I'm going to set Q1 equal to 1. That means that the vector Q is equal to 1, 1, 1. So now I have all three vectors that I need to form my three solutions. Okay? Now, we have to be careful because x1, x2, so my x2 will look like this, my x3 will look like this. Those are all going to show up in the linear combination. So what is x1 equal to? x1 is this first matrix right here. 1, 0, 0, times the exponential e to my eigenvalue, which was 4t. What is x2 equal to? Well, x2 is equal to, again, we're using this right here, kt exponential plus e exponential. K2 is going to equal 1, 0, 0, there's k, t, plus 1, 1, 0, there's p. And I'm just going to bring the exponential out just for simplicity, e to the 4t. What is x3 equal to? Okay, well, x3 is going to equal, again, using now this formula down here, 1, 0, 0, t squared over 2, plus 1, 1, 0, t. My t's and my pluses look very similar, so I have to be careful. Plus 1, 1, 1 times the exponential e to the 4t. Okay? So putting these together into a general solution, I get x equals c1, remember we need our parameters, times 1, 0, 0, e to the 4t, plus c2, 1, 0, 0, t, plus 1, 1, 0, e to the 4t, plus c3 times 1, 0, 0, t squared over 2 plus 1, 1, 0, t plus 1, 1, 1, e to the 4t. Okay? That's my solution. All right, yeah, it's involved. It's an involved process. The answer looks very big and intimidating, but the actual work that went into this, as far as the looking at comparing this to some of the more complicated problems we've done, it wasn't too bad, especially if you're comfortable working with augmented matrices. These kind of this kind of notation here. We have another example to do with repeated real eigenvalues. I'm going to do that in the next video.